Let's start with you telling us a little bit about you and your career to date. So where did you get your education from, and what was your PhD on and things like that?
I started doing computer science in Spain, and then I started my PhD, and it was about augmented reality and serious games. And that's when I decided to do an internship here in Bristol. And because I've been working with augmented reality, that is manipulating virtual objects inside the real world, I had some experience about, how you can position, rotate virtual objects. And that's when I saw acoustic levitation, the possibility of having real objects in the real world. So the objects, they are no more virtual, they are real objects that you can move in 3D and rotate in 3D. And that's how I moved from computer science more into mechanical engineering or physics.
And how long have you been at Bristol now?
It has been 3 years.
Yeah. So can you tell us about your present study into sort of levitating and how it came about?
So, as I said, it all started when I wanted to move from virtual objects to real objects. And I thought that acoustic levitation could be a good way to position and orientate objects in real life. And currently I have several research lines. One of them is being able to levitate big objects, because so far acoustic levitation, you levitate particles that are around 1, 2, 3, 4 millimeters, maybe up to 1 centimeter are the largest ones. So that's one research line, trying to levitate large objects, because of course for seeing objects you would like them to be big. And the other research line is a little bit different. Instead of levitating only one object, you levitate loads of tiny objects and they create different shapes. So you may have, let's say, 100 particles that you can position individually, and they are like physical voxels that create the objects.
And you mentioned that you start off in the computing space, so what would be, for the lay person, what would be the crossover between the two disciplines, if you like?
So I think there are two crossovers. One was the idea that with the computer, you are used to manipulate virtual objects in 3D. Like you don't need to be restrained to gravity or other physical constraints. So you are used to get an object, move it in 3D and also orientate it. And then when you move to the physical world, you have all the techniques that you can apply. And previously, if you were a physicist or a mechanical engineer, you had no experience with manipulating objects in 3D. But here, because we were used to work with virtual objects, we had some interaction techniques. And the other crossover point was using computer science as a tool to visualize the acoustic field. The acoustic field is great, it can manipulate particles, but one problem is that you cannot see it. So simulations really help to understand what's going on.
So how do you create the conditions whereby small objects can move around using the acoustics?
So we use ultrasound, first of all. Otherwise, if we use audible sound, which is possible, you can levitate objects with audible sound, but the experiments would be very deafening. They would be dangerous for your health. So that's why we use ultrasound, because they don't interfere much with your hearing. And basically, the simplest way of levitation is having an emitter going from one direction, an opposed emitter going from the other, and that creates a standing wave. And in those nodes, you can put particles. This is basically the principle of acoustic levitation.
And so what are the biggest challenges you're facing at the moment with this kind of work?
So the main challenge is being able to levitate multiple particles. For that, instead of only having 2 emitters, you have, let's say, 512 emitters, maybe half on this side and half on this side. And you control individually which signal each emitter is emitting. So with that, you can engineer the field, and that's basically the main challenge. What phases or what signals should you play in all the speakers in order to create the field that you like? That is the field that would trap the particles at the positions that you want.
And what are the next steps in your study then? Where do you want to take this next?
So I think all the studies that I've done, they are working in air, levitating particles in air. I think I would like to move towards levitating or trapping things in water. And people may not be interested because things in water, they are much smaller. You trap things in the micrometer order. So these things could be cells or they could be micro drag capsules. But I like working in water because if things work in water, they should also work inside your body. Mechanically speaking, water and your body is pretty much the same. So if you are able to levitate particles in water, you should be able to levitate particles that are inside your body from the outside.
Just a thought that's crept into my head just then when you were talking about moving objects in water. Do you think acoustic technology at some point in future could be used to help move very small particles of plastic in the oceans and that around? Do you think
So
that could be?
that's a very good question, because one research line that we had is being able to attract particles towards the source. You know, in acoustic levitation, it's quite easy to push the particles or also to trap the particles when they are sandwiched between emitters. That is, you have emitters on both sides. But you can also, we proved that it's possible to attract the particles towards a single source. And we call these things tractor beams. Basically being able to attract a particle towards the source. And that's very useful for what you mentioned, like being able to go to the ocean and one of the boats is emitting a specific type of wave, a tractor beam, and then all the tiny particles or also oil spills, they are attracted and gather towards the boat.
So, I mean, you've got some great industrial applications of the work. So what are you most excited about regarding your particular field of study at the moment? What's really getting you out of bed in the morning?
So I think I'm glad because we are about to finish what we wanted in the project, the capability of moving multiple particles individually. So we achieved that and we recorded some nice videos, and probably soon this thing will be published, and basically I will achieve what I was being paid for. And I think I'm excited about starting new things. I think as a researcher, you should always be excited about new things, about pushing the boundaries.
So are you collaborating with anyone? Obviously you're collaborating with the university here, but is there anyone else that you're collaborating with on these projects?
Absolutely. So most of the research that I do, they are actually in collaboration with other fields. So for instance, we do a lot of spectroscopy or characterizing levitated samples, and for that we need to work with physicists.
So who's currently funding the work?
Currently I am funded by EPSRC, that is the UK organisation that funds engineering projects.
How difficult have you found it to get funding for this project? And I mean, I know funding is changing because of the EU and Brexit and all this sort of thing. Has that affected you, or had the funding already come through at that point when Brexit was announced, etc.?
I think in my case, I had the funding before Brexit, so I haven't had any problem regarding Brexit.
So when you're not up to your elbows in mechanical engineering and related research, what other things do you like doing out of the lab?
So I think mainly I like music. I like playing the guitar, which is again related to sound probably. I also like jogging, but most of my hobbies, they are actually related with engineering or physics. So of course I started doing computer science, but I've always been very interested in electronics, physics, mechanical engineering and these sort of things.
You said that you're going to go back to Spain, so are you going to be continuing in this field there? And what were your thoughts? What are you going to plan to do there when you get back to your current country of origin, as it were?
Mm-hmm. So here at the EPSRC that funds me, I'm funded to create display technologies, to create devices that can levitate particles to display objects. And I think when I go back to Spain, probably, as I said, I will focus more on small particles in water, mainly working in water. So I will move from displays probably to applications in medicine, and also, as you said, trying to clean the oceans. In general, I think I would try to connect more with the industrial applications.
You also mentioned the human body, so you're also thinking in terms of nanotechnology, of being able to move things around in the human body?
Yes, but I don't know if I would go nano. Probably the scale of the things that you can manipulate with acoustics inside the body would be around the micrometer scale.
Going back to your work on augmented reality, now that's becoming quite a significant part of the way the industry is going, particularly with you mentioned gaming and stuff like that. So what you've obviously been keeping abreast of what's going on. What are your thoughts about where augmented reality is going at the moment?
So I think when I started doing research in augmented reality, that was 2012, it was still maybe a little bit new, the devices were still not fully ready, whereas now devices are totally capable of doing augmented reality. Not only your computer or specific devices, but your mobile phone is a perfectly capable platform. So I think we will be able to see it more and more around, not only for games, but also for applications such as mapping, advertising, do-it-yourself, like maybe you can measure distances in your wall, design in general.
And did you touch on virtual reality in your previous work, or is that something that you didn't touch on?
So we have done a little bit of virtual reality, mainly to compare levitated systems with virtual systems. You know, like you have a levitated physical particle and you can move it around. So how accurate are you moving this particle, this physical particle, compared to a virtual particle? So I've done a little bit of virtual reality, but always as a secondary objective.
So have you got people working with you and for you here at the moment, and how big's your team here?
So the team, basically we are between two teams. This one is computer science, whereas I also go to mechanical engineering, and they are quite big teams, but they are not all working in acoustic levitation. I think in mechanical engineering we are around 5 or 6 people working in acoustic levitation. But I also have some external collaborators. I also collaborate with other universities.
Okay, so you mentioned the do-it-yourself acoustic levitation devices. So how easy are they to put together, and would people need to have a bit of mechanical engineering knowledge, or could I just order the equipment in, or the bits and pieces I need, and put it together in a few hours? How does it work?
Mm-hmm. So basically the kit is a simplified version of the devices that we have here, and you can go to the internet, search do-it-yourself acoustic levitator, and you will have a part list. This part list is quite simple to get. You can order the components in Amazon, and then you also have a video, a step-by-step video on how to put it together. And you will need a little bit of skills with Arduino and soldering, but everything is provided. In fact, we have done this thing with 12 years old students and also 11 years old students, and we gave them the things, and basically they put together one acoustic levitator to teach them a little bit about electronics and in general acoustic levitation.
You just touched on working with school children, so is that something else you do? You do stuff within the community to encourage youngsters to get into engineering? Is that something you do?
Yeah, a lot. We do a lot of public engagement, not only just giving talks, but then we go to schools and we teach them how to build this acoustic levitator, so they practice a little bit of electronic engineering, mechanical engineering, and basically giving them the opportunity to do some hands-on experiences.
Slightly unrelated question is, why do you think it is that there aren't more women coming into mechanical engineering and information technology? What do you think is putting them off?
I think a large tradition of mainly males doing this subject, and I think that could be scary. And also the TV was always showcasing like men, most of the figures they were men, but I think we are doing a great effort trying to change that. So this is one of the levitators, and we have waves coming on from the top and waves coming from the bottom, and that basically creates a standing wave that if we get some particles and we put them around, they will get trapped at the nodes. And the good thing about this levitator is that it's strong enough to levitate these light particles, but it can also levitate liquids such as water.
So you're creating the sound waves through these transducers down here and up the top here?
Yeah, we call them transducers. It's just a fancy word for speakers.
Okay. The power of the speakers you can increase by increasing the voltage?
Exactly, voltage is proportional to the power. So more voltage, more strength to trap particles, and that's good for liquids. But if we increase the power too much, you can see that the droplets are getting squashed, and then eventually they pop if we apply too much force. So levitating solids is super simple. You just put as much power as you want, but levitating liquids is a little bit harder because you need to know how much power you should apply. If you apply too much, they will pop. If you apply too little, basically they will fall.
So if you ever get around to levitating humans, you need to bear that in mind.
Exactly, yeah.
You don't want people popping.
Yeah, and we are quite squishy, so that's
a lot of water.
So this is one of the main applications of acoustic levitation. It's called spectroscopy. Instead of having your sample on a slide or a surface, you have it levitating, and then when you shine light, you can analyze what passes through and what gets reflected. And you know that all the reflections and all the transmissions are going to be from the sample and not from the holder.
So, how quickly would the levitation stop if you interrupted by running your finger across the top? Take it needs pretty much constant agitation, should we say.
So if I put my finger here, the most dense particle, the water droplet, probably will fall. It doesn't have enough energy, you see it gets heavily distorted. But it's still okay, like sound can diffract around my finger. That if I put more in top, see it falls, and then also this top one, the big one falls. But in general, you can move small objects around the thing. Sound will diffract around them, and then they can still be levitated. If you want, we also have the portable version.
So I guess with that version, the signal is, because with this person it's trapped between two beams. With this one, is it just beams sort of cross over and hold it?
It's sort of like two fingers pinching the particle.
Okay.
And the cool thing about this is it's very weak. It can only levitate the styrofoam, but the good thing is that it should like completely work upside down.
What are the limitations to levitation, man? What's the largest particle size or object you could levitate?
So there are two limits, and one is the weight limit, but you can surpass that with more power. More voltage means more power, and then you can levitate heavier objects. But there is another fundamental limit, and it's the frequency. The maximum size of the object, it's half of the wavelength. And that means that given a frequency and a medium, let's say 40 kilohertz in air, you get 8.6 millimeters wavelength. That means that you cannot levitate anything larger than 4 millimeters. So for levitating large objects, you would need to decrease the frequency. But then it would become audible, so it would be unfeasible. So this is the simulator that we use, but now everything is empty. We will load a file, the simulator, and now we can see different things. So all these tiny things, they are the speakers, the transducers, and the color that they have represents the phase or the signal that we send. We could put a slice of the field, so this is a slice passing through the center, whereas basically the dark areas mean very low intensity, or if we could hear the ultrasound, it would be quiet sound. And the bright areas, they mean high intensity, or if we could hear the sound, it would be loud areas. The particles, they are trapped actually here in the nodes, in the quiet areas. And the good thing with this thing is that we can move the slice around, like we can move the slice, push it back, move it forward, and we can also change the signal that the transducers are emitting. So if we select all the top transducers and change the phase, we can see that the standing wave is moving upwards. And with that, we can move the particles. If there were particles trapped in these dark areas and we change the phase, the particles would go down. Another thing is that if you have individual control on each of the transducers, you can actually refocus not only along a line, but at any point that you want. So you could press at any position, and you could see that wherever I press, I could focus there and I could trap the particles there. Not only in 1D, but also in 3D. But for that, you need individual control. You can see that when I press click here, all the phases of the transducers change.
I guess that will have more relevance for industry, won't it? If you can be more specific where you can move objects from and to.
Yeah, absolutely. We have some applications, pick and place machines for PCBs, printed circuit boards. You know, you have these suction pumps now that they pick the components. So we wanted to levitate the components and move and orientate them to different positions. And it's good because they can be as small as you want. You know, like you don't have any problems like picking them up and moving them.
So did you develop this software yourself, or is this something you managed to get off the shelf?
No, it's a software that across the years I've been putting together. So it started like very small code and then keep adding more and more things. And it's basically what we use now to simulate and also to control the devices. It can simulate and also control the devices.
Hence your background in computer science coming back to help you.
Yeah, exactly. I think that it was very, very fortunate that I was a computer scientist because I could put these simulations together quickly.
And would you have had to outsource that if you hadn't had that knowledge yourself? Would you have had to collaborate with a computer scientist?
So I think a mechanical engineer or a physicist, probably they would try to use already made software. But then, of course, it's not as versatile as you want. You know, if you use pre-made solutions, they are designed for a specific thing. Whereas if you can make it yourself, you can tune to what you exactly want.
Yeah, it becomes bespoke to your
Exactly.
project.
For us, it was more about being it real time, being able to move, change the signals, and seeing it in real time, not having to press simulate and then wait for half an hour or whatever. So these are some of the devices that we are putting together. And as you can see, they have one wire going to each of the speakers. And that's to have individual control on the speakers in order to move the particles wherever we want. In contrast, this one that was the device that we were seeing, the one that people can put together at home, this one only has one signal going to all the transducers. And that's just because you use one levitation and you will have no control on the position of the particle. Of course, having more channels mean more complex electronics, like this one. The electronics for this one, they're just this, an Arduino and a motor driver to amplify the signals, whereas this one have like FPGAs and lots of individual amplifiers for each of the channels.
And what was the one you had over there, looked like the headdress? How does that one work?
It's like this one is just a different arrangement of transducers to basically manipulate things in a plane.
So how long does it take you to build one of these?
So I put some of them together myself, but we collaborate, but it takes a long time, not just because the building, like probably 2, 3, 4 days, maybe a whole week, but just because then you need to check all the channels and you need to calibrate all the channels. It's not only about building, it's also about calibration.
And how do you calibrate each of the channels then?
So in the beginning we had a manual way, like basically we go transducer by transducer and we measure how much is outputting, how much is deviated, but now we are trying to apply a semi-automatic way, whereas we put only one microphone here at a known position and then they all fire sequentially and the computer will calibrate the things, and that would speed up things a lot.
And again, for the computer that's calibrating it, is that based on software that you developed?
Yeah, we use the same software for everything, like simulating, controlling the things, calibrating.
Cool.